Hello and welcome back to Math with Mrs. Becker. Today we are looking at college algebra and we are starting chapter 2, section 2, where we focus on polynomials that have higher degrees. I know we've already looked at linear functions where you have a degree of 1. We have studied quadratics where you have a degree of 2. Today we're going to kick it up a notch. Let's get going. When you graph a polynomial function, you get a graph that is continuous. And what that means is that you can draw the graph without lifting up your pencil because there are no breaks, no holes, or no gaps. Okay, so informally, you can say that if a graph is continuous, you can draw it with your pencil and you never have to lift the pencil up from the paper. Another feature of a graph of a polynomial, it only has smooth rounded turns, meaning you cannot have any sharp points. Okay, let's go ahead and look at transformations, of course, right? Transformations of higher degree parent functions. So the first one, they want us to graph f of x if our f of x is equal to x to the power of 5. Now notice they did not give us any ordered pairs. So what we have to do is go ahead and create our own XY table. Now typically a rule of thumb is that you want to go from like -2 to 2. And the reason why is because you can see what's to the left side of the y-axis, right on the y-axis as well as to the right. You get to see this side, what's happening here, and what's happening here. Now to find your y value, remember you just go ahead and plug this value into the function. So -2 to the power of 5, -2 times -2 times -2 times -2 times -2 is -32. -1 to the power of 5 is -1. 0 to the power of 5 is 0. 1 to the power of 5 is 1. 2 to the power of 5 is 32. Now, obviously, I can see that this is going to go way off the graph. The idea here is just to get the general shape. So when I go ahead and I graph this, -2, -32. So I'm just going to go ahead and put a point way off the graph because I know that -32 would be there. -1, down 1, 0, 0, right 1, up 1, right 2, up 32, so I know without a doubt that that would be way, way high up there. So I could go ahead and sketch it so we can see. And the reason why I wanted to include those other points, if I just did these 3, you may think that it's a line, but by knowing that when I go 2 over, there is a significant jump. That helps you to know that you really do have that sharp curve upwards. Same thing here. When I go ahead and I just look this way, you might think it's a line. But by knowing if you go to the left too, it really drops down, that helps you to get that curve shape as well. Okay, so that is the first part. How can you graph a parent function, even if it has a higher degree? Go ahead and make XY tables. Now they're going to do transformations, because that's what algebra is all about. So if I have g of x, and g of x is -x to the power of 5. Remember, whenever you have a negative, the transformation is a reflection. If it is out front, not in parentheses, it's a reflection over the x-axis. And the way that you change the ordered pairs, if it's a reflection over the x, is you keep the x value the same, you change the y. So I can take these ordered pairs, and I'm keeping the x the same. -2, -1, 0, 1, and 2. Again, to reflect over the x, I change all the signs of the y. -32 becomes +32. -1 becomes +1. 0, there's no such thing as a -0, so that just remains its original value. If I change a 1 to a -1, +32 becomes -32. Now what you want to do is graph it on the same grid. So I go to the left 2, up way high. I go to the left 1, up 1, 0, 0 stayed right there. go to the right 1, down 1, go to the right 2, go down 32. So again, the reason why I wanted to make sure that I did more than just those 3 points, where it looks like it could be a line. But then notice, in order to get that point that's way off the graph and this point that's way off the graph, we had to go ahead and curve it. So what you're doing here is graphing an original function by creating ordered pairs. Then you identify the transformation that occurred, change the ordered pairs, graph on the same grid. Let's go ahead and do it again because that was so much fun. Okay, so this time, my parent function, the mamas and the papas, the parent function is x to the power of 4. Again, they did not give us ordered pairs that they wanted us to use, so I'm going to fill in -2 all the way up to +2. If I take -2 to the power of 4, -2 times -2 times -2 times -2, that's +16. -1 to the power of 4. If you take -1 times itself 4 times, you get a +1. 0 to the power of 4 is 0. 1 to the power of 4 is 1. 2 to the power of 4 is 16. So you go ahead and you sketch the graph on the grid. So I go the left 2. This is 1, 2, 3, 4, 5, 6. So I know it's going to be way the heck up here. Totally fine. Go to the left 1, up 1, 0, 0. Right 1, up 1. Go to the right 2 and off the graph, but it's all right. I provided a graph just to save you time, but not everything's going to fit on that. Okay, now here is g of x. So let's go ahead and look at g of x. It's x to the power of 4 plus 1. You have to identify the transformation that occurred. Anytime you are adding or subtracting, it is a slide. If it is not in parentheses, it's vertical. So this is a vertical. You can call it a shift. You can call it a slide. You can call it a translation. Vertical lines run up or down. So this can only be going up or down. Because it's +1, we are going up 1. The way that you change your ordered pairs, it's vertical, so it changes the y. If I want to go up 1, I take the y's and I add 1. So to get g of x, I keep the x's the same. -2, -1, 0, 1, and 2. I take all of the y's and I add 1 unit. 16 plus 1 is 17. 1 plus 1 is 2. 0 plus 1 is 1. 1 plus 1 is 2. 16 plus 1 is 17. Now sketch g of x on the same grid. So I go to the left 2 and I go up higher than the one that was way off. If I go to the left 1, I go up 2. Stay at 0, I go up 1. Go to the right 1, go up 2. Go to the right 2, higher than my point that was off of the grid. Go ahead and connect them. So it's the same shape, the same size, it just shifted up. Guess what? We get to do another one. Because now they said, hey, what if we have h of x? And h of x is x plus 1 in parentheses to the power of 4. So h of x is this, x plus 1 to the power of 4. Remember, anytime that you are adding or subtracting, it is a shift, slide, or translation. Okay, they all mean the same thing. If it's in parentheses, it's horizontal. So this is a horizontal slide. Your formula for horizontal, it's always x minus h. Because this is a plus 1, what that means is you minus the -1. Negative direction means that you're actually going to the left 1. So to change the ordered pairs, it's horizontal, so you change the x. To go to the left, that's the negative direction. So I take all of the x's and -1. I am not making a vertical change, so I keep it at y. Now here's the deal with this. We are changing f of x. It says h of x is a transformation of f of x. So I need to take my original points to make this, because h of x is a transformation of the parent. So I take the original ordered pairs. Take every x minus 1. -2 minus 1 is -3. -1 minus 1 is -2. 0 minus 1 is -1. 1 minus 1 is 0. 2 minus 1 is 1. I am keeping the y's. So 16, 1, 0, 1, 16. If I graph this, I go to the left 1, 2, 3, go up all the way to where I had marked 16. That's my original point. If I go to the left 2, I'm up 1. If I go to the left 1, I'm at 0. 0 I'm up 1, 1, I'm up 16. So I go ahead and I plot. Notice it's the same shape, the same size. What happened is we just shifted it to the left one. Okay, so transformations, just like we've been doing all year so far. Now in Algebra 2, we talked about something called end behavior. Now end behavior tells you what happens at the end of your graph. What happens all the way to the right or what happens all the way to the left. And the way that you determine that is by looking at the leading coefficient and your degree. So let's look at 2. Your leading coefficient, what that is, when you make sure that your polynomial is in standard form, 3x's, 2x's, 1x's, no x's, we are good to go. The leading coefficient is the number out front. This determines what happens with your graph as you go all the way to the right. So you write it as x approaches positive infinity. As your x values go all the way to the right, your polynomial does what? If your leading coefficient is positive, the arrow will be going up to positive infinity. If your leading coefficient is negative, your arrow will be going downwards to negative infinity. Our leading coefficient is positive, so as we go to the right, the arrow points up. Now your degree. Remember, the degree is the highest exponent that we have on our variable. Our highest exponent is a 3. 3 is an odd number. The degree tells you what happens as you go to the left. So as x approaches negative infinity, as we go all the way to the left, your polynomial does what? And it's either arrow up or arrow down. 3 is an odd number. Odd degrees have opposite end behaviors. So if this arrow was going up, this arrow would be going down. I'm hoping even just seeing this, it kind of brings you back to Algebra 2 when you remember that. If not, we still have another example. Okay, leading coefficient. 4x's, 2x's, no x's. So it is in standard form. Your leading coefficient is the number out front. In this case, it's a -1. Your degree is the highest exponent on the variable. It is a 4. Now the leading coefficient tells you what happens as you go to the right. So as x approaches positive infinity, this is the fancy way of saying, hey, as you're going to the right, your polynomial, because your leading coefficient is negative, your polynomial ends going downwards. As you go all the way to the right, the last thing you're going to see is an arrow going downwards. Now to the left, as x approaches negative infinity, now this is based off of the degree. 4 is an even number. If this is an even degree, both sides have to do the same thing. You need to keep it even. So if this arrow is going down, this also has to go down because this is even. Okay, so that's what end behavior means. Okay, the next part. They want to talk about the zero of a polynomial. Now, in order to find the zero of a polynomial where you can find your solution using algebra skills, is you take the equation and you set it equal to 0. Now that makes sense. To find a 0, set the equation equal to 0. Then from there, you can factor, you can do the quadratic, you can do all those different things. And what your answers are, they are the x-intercepts of the graph. And so we're going to go ahead, find the zeros using algebra, and then we're going to go ahead and graph on Desmos to check our answers. So here we go. If I want to find a 0, what I need to do first is set the function equal to 0. That's the first thing you need to do. So we did that. Now I want to factor it. If I look at all of those terms, they all contain an x. So I can take an x out. If I had 3 x's and I take one out, then I'm down to 2. Minus, if I had 2 x's, I took one out, I'm down to 1. Minus, I had 2 x's, I took one out, I'm just down to the number 2. Now here I can factor this. I have the x out front still. 2 numbers that multiply to -2 and add to a -1. Well, that's x minus 2 and x plus 1. Again, keep in mind we're finding zeros. So this whole thing is set equal to 0. Now to find your solutions, you take each piece. So x equals 0. X minus 2 equals 0. And x equals -1. Oh, sorry. I did the math already in my head. So x plus 1 equals 0. Now you solve for x. Here, x is already by itself. Here, if I add 2, x is a 2. If I took my x plus 1, I would minus 1, giving me x equals negative 1. So those are my zeros. Now to check it, go to Desmos, x to the power of 3 minus x to the power of 2 minus 2x. So I just graphed the original. Here is my graph. I can see that, yes, I do have 3 zeros. You go ahead and tap those. Our x value should be negative 1, 0, and 2. Negative 1, 0, and 2. So our answer's checked. Okay, let's look at another one. If we want to find the zeros of negative 2x to the power of 4 plus 2x squared, step 1, you have to set it equal to 0. Now here I can factor this. I don't like having my first term negative. So since I'm factoring anything or factoring something anyway, I'm going to go ahead and pull that negative out as well. Negative 2x squared is coming on the outside. Negative cancels a negative, 2 cancels a 2. 4x's minus 2x's, I would have 2. Positive divided by a negative is a negative. 2x squared minus, or 2x squared divided by 2x squared. If you have the same thing on top and bottom, it's a 1. It's the same thing as like if you said 5 goes into 5 how many times? It doesn't cross off and go away. This is 2x squared divided by 2x squared. How many times does it go into itself, basically, and that's a 1. I can factor this further. This is the difference of squares. So I would have negative 2x squared, x plus 1, x minus 1. Now I can find the zeros by taking each piece separately. Negative 2x squared, set that equal to 0. X plus 1, set that equal to 0. X minus 1, set that equal to 0. Now here you go ahead and divide by negative 2. That will leave you with x squared. 0 divided by negative 2 is 0. When you take the square root, what happens is you end up with a plus or a minus typically. The square root of 0 is just 0. There's no such thing as a positive or a negative. So this forms what's called a multiplicity. 0 happens twice. So x equals 0 multiplicity of 2 because the same answer occurred twice. Because they're saying positive 0 and negative 0. Well, there's no such thing as a positive or a negative 0. So what really happened is 0 happened twice. Okay. Here, I would minus 1, so x equals negative 1. Here, I would add 1, so x equals 1. So my graph should touch or cross at 0, negative 1, and 1. So to check our answers, we need to go into Desmos. Let's get rid of that graph. I will go ahead and put in this one, negative 2x to the power of 4 plus 2x squared. So here is my graph. I have 1, 2, 3 locations. Your x values are your zeros. Negative 1, 0, and 1. We had negative 1, 0, and 1, so we're good to go. Let's look at one more, and then we're really going to focus on that multiplicity idea that just occurred, okay? Find all of the zeros of x squared minus 81. Step 1, to find zeros, you set it equal to 0. X squared minus 81, I can go ahead and take the square root of each side. The square root of x squared is x. The square root of 81 is 9. So this is x plus 9, x minus 9 equals 0. Well, if I take x plus 9 and set it equal to 0, you would have to minus 9 to the other side, so x equals negative 9. If I set this equal to 0, I'd have to add 9, so x would equal 9. So there are my two solutions. Now to check it, go into Desmos. Let's go ahead and graph. X squared minus 81. Now obviously I don't see anything, but if you look at my window, it was zoomed in pretty tight. So if I'm looking at my zeros are at 9 and negative 9, you have to make sure that you have your window so it does show 9 and negative 9 on the x-axis. So when I zoomed out, yes, we do have the graph there. My solutions, there they go. My solutions are negative 9, positive 9, and that's what we got. Okay, now multiplicities. There's this thing called the fundamental theorem of algebra. And what it tells you is that you have to have the same number of solutions as whatever the degree of the polynomial is. And that's where lots of times people get confused because you may have to have 5 solutions, but when you go to solve it, you only get one number. Well, you might have that solution as a multiplicity of 5, meaning if you go and solve it all together, let's just say it's a 1, you might have x equals 1, x equals 1, x equals 1, x equals 1, x equals 1. Okay, so when that happens, if it's more than once, it's called a multiplicity. Now your multiplicities, what they do is they determine what happens at the x-axis for that solution. If you have a multiplicity of 1, and what that means is that solution occurs only once, your graph will cross the x-axis. It crosses right through it, crosses the x-axis straight. So it is a straight line if that answer happens once. If you have an even multiplicity, let's say multiplicity of 2 or multiplicity of 4 or multiplicity of 6, what happens is your graph will bounce off the x-axis at that point. It will not cross it. At that answer, it will hit the x-axis and bounce off and go back the way that it came. If it's an odd multiplicity but greater than 1, because remember, if it's 1, it crosses straight. If it's odd greater than 1, it crosses and bends. So if it was crossing here, it would bend at that exact point. That's what that means. Where if it's straight, it's just a straight line. If it's even, it hits it and bounces back. Okay, so let's go ahead and find our solutions, look at the multiplicities, and then graph them just to kind of see what it looks like. If you want to find the zeros, step 1, 3x4 minus 4x cubed. To find zeros, you need to set it equal to 0. I can factor out 3 x's because this has 4 x's and this has 3, so I can remove 3. This leaves me with 3x minus 4. Once it's factored, you take each piece. So x cubed, that equals 0. 3x minus 4, that equals 0. Now, x cubed equals 0, that means x equals 0 3 times. So this is x equals 0, multiplicity of 3. You have to get 3 answers out of this because it has a degree of 3. They're all going to be 0. Here I add 4 and divide by 3, so x equals 4/3. This is a single x. It has a degree of 1, so it's a multiplicity of 1. So when we graph this, our graph should have a line that cuts through 1 1/3 straight because of the multiplicity of 1, and it should cross and bend at 0. So let's check it out. I'm going to go ahead and get rid of this graph. I am looking at 3x to the power of 4 minus 4x to the power of 3. So if I look at this, I'm going to go ahead and even zoom in a little bit. So here, at this point, it's 1.33. So that's my 4/3. It crosses and it stays straight as it crosses. Now here, this is what they mean by a bend. It crosses, but it definitely has a little bend there. This is because this has a multiplicity that is an odd number bigger than 1. Our solution should be 0 and 1.3 repeating, which is the same as 4/3. Okay, let's do one more. Find all the real zeros. So I set the polynomial equal to 0. Step 1, if I'm going to factor it, I do notice that all of these terms contain an x. So I can take x out, leaving you x to the power of 4 minus 6x squared plus 9 equals 0. Now remember, if you have 3 terms and the exponents are 4, 2, and 0, you can still do the multiply add method. But what happens is you have x squared instead of just an x, because the amount of x's you have doubled from when you typically just do multiply add method, because normally it's 2, 1, 0. Well, this is 4, 2, 0. So the amount of x's was doubled in each location. So you double the x, or take it to the power of 2 when you are factoring it. So we have to remember we still have our x out front. 2 numbers that multiply to 9 and add to a -6. Well, that's -3 and -3. And again, this is all equal to 0. So x equals 0, x squared minus 3 equals 0, x squared minus 3 equals 0. Well, here, x is already by itself. Here I would add 3, so x squared equals 3. Take the square root of each side, so x equals plus or minus the square root of 3. Here, same thing, add 3, so x squared equals 3. Take the square root of each side, so x equals plus or minus square root of 3. So here are my solutions. X equals 0, that only happens once, so it's multiplicity of 1. Now, x equals a positive square root of 3, it happens here and here. So it's a multiplicity of 2, so that's even, it's going to bounce. Okay, if I go ahead, I'm going to zoom this up a little bit so you can see this better. Okay, so I have x equals a negative square root of 3. There's a negative square root of 3. There's a negative square root of 3. So I actually have a multiplicity of 2. So I have 1, 2, 3, 4, 5 answers. That's what I needed because my original problem had a degree of 5. Graphically, what's going to happen is my graph should cross as a straight line at 0. When I look at a positive square root of 3, which is approximately 1.7, it should bounce. When I look at a negative square root of 3, which is approximately negative 1.7, it should bounce. Let's go ahead and see if that's what happens. So I had x to the power of 5 minus 6x to the power of 3 plus 9x. Whoa, okay, this graph is really cool. Check that out. I love it. Okay, so what happens at 0? That was our multiplicity of 1. Notice it stays straight as it crosses through. Here's my 1.7. Multiplicity of 2, so it bounces. Here's my negative 1.7. Multiplicity of 2, so it bounces. So the number of times an answer occurs, that determines what happens at the x-axis at that 0. Okay, last little bit. They want us to use a graphing utility to find zeros. Round any to the nearest hundredth. So basically, you guys, this is just more practice on Desmos. X to the power of 5 minus 3x to the power of 3 minus x to the power of 2 minus 4x minus 1. So they want us to find the zeros. Well, remember your zeros, I'm just going to zoom out and make sure that I have it here. Okay, your zeros are where your graph would cross the x-axis. So you're rounding to the hundredth. So x equals negative 1.86. X equals 2.12. Let's make sure I get the right, oh, that one. Okay, sorry, here we go. So negative 1.86 is that point. I'm going to turn that one off. Now I want this point. X equals negative 0.25. Turn that one off. X equals 2.12. So if I zoom out even more, you want to make sure we didn't miss any. We did not. So those are our zeros. Zeros, what that means is it's where it touches the x-axis. Now some of you are probably going, well, wait a minute. And I hope you are saying, wait a minute. We need 5 answers. We only have 3 answers. That crosses straight, that crosses straight, that crosses straight. So I hope you're like, Becker, what the heck? Because that is what you should be saying. Because we should see 5 answers here. Because we don't, that's where imaginary numbers come into play. Because they make sure that you can find this many answers. So here we needed 5. There's only 3. So if we actually calculated this out, there would be 2 imaginary solutions that are still technically solutions. You just can't see them on the graph. That's kind of your little hint of what's coming. Our imaginary numbers are coming up. Okay, let's do one more. Let's graph negative 3 divided by 8. Whoa, there we go. 3 divided by 8. Go ahead and I hit the over arrow. It is x to the power of 4 minus x to the power of 3 plus 2x to the power of 2. That's a lot of exponents. Plus 5. Okay, so here, whoa, look at that graph. You guys, these are so cool. I hope you're having fun today. Okay, so here are my graphs, or my graph. What I want to do is find the solutions. So x equals, they said round it to the hundredth, negative 4.14. The other one, x equals 1.93. So again, you might be looking and saying, hey, that's a straight line, that's a straight line. It's definitely not bending as it crosses the x-axis. That means this answer happens once, this answer happens once. I need 4 answers. You guys, the other answers are imaginary, and that's what we will get to later this week. I hope you had a great day. Here is a suggested assignment if you need more practice on multiplicities, zeros, working on Desmos, transformations, lots of practice for all those different things. Again, I hope you had a great day, and I'll talk to you soon.